Okay, so now that we have started to define the main curves of our project, one thing we need to always keep in mind is to understand the difference between modeling something digitally and creating information that can actually be manufactured and built. So in this case, we have to start making sure that our geometries are constructible and that they comply to some fabrication constraints. For example, in our previous video, we created this collection of interpolated curves to define the shape of our stadium. And while these are perfectly valid geometries in our model, these curves are not something we could normally use, taking into account the constraints we need to look up while we're gonna build something. So, for example, if we take a look to our curves or splines, we'll realize that there is not a proper way of dimensioning under normal procedures. And to explain this better, let's take a quick look to a geometry concept called curvature. Okay, let's say that we have a planar curve C, and let's say that I want to evaluate it at a point P. What I could extract from here is a curvature value of that specific point in my curve. And a simple way to understand this is that at any given point on a curve, there is a unique circle which most closely approximates our curve at that specific point. So here on my top view, I'm gonna go ahead and create a spline similar to the ones that we already have. And then I'm gonna try to measure the curvature of it. So I'm gonna type the command radius. And then if I move my cursor over the curve, you'll notice that we'll have several circles with different radiuses adjusting to the curvature at that specific point. For example, at one point I have a radius of 71, and immediately after I have one of 49, then 36, and as you can see, this value is changing at every different point, so this becomes a problem as we cannot specify a constant dimension or distance to build our elements, especially for structural elements where everything needs to be represented with precise dimensions. So here's when an important part of computational design takes place, which is the performance of geometry optimizations for fabrication. So in this particular case, what we will have to do is to rebuild or optimize our curves so we can be able to represent them in a proper way. For example, decomposing these curves, evaluate it, and rebuild it using only arc segments that we can easily represent. So let's take a look to a quick graphic representation of how we're gonna do this. Okay, so we're gonna start again with our planar curve C, and then we're gonna go ahead and create a set of sample points to evaluate the curvature at those particular locations. So then, as you may have guessed, we're gonna have several different curvature values or circles at each one of our points. Now, depending from the different curvature values we get from these circles, we're going to remap the location of our points using some mathematical functions, meaning that the location of our original sample points will change. So the zones or areas with more curvature will have points closer between them, and the zones with less curvature will have the points more far away. Then we're going to split our original curve at these new points to have a new set of segments which we're going to evaluate and extract the middle point of each one, something more or less like this. And once we've done this, we're going to create a collection of 3 points with the start point, middle point, and end point of each segment, which we will use to create 3-point arcs. So this will reconstruct our curve with different arc segments we can easily represent. Okay, so while this procedure I have just explained it can be easily done using normal Grasshopper components, I'm gonna take this opportunity to dive with a special component available for Grasshopper, which is the Python scripting component. And for those of you who might not know or are not familiar with scripting, Python is a very flexible and powerful programming language, and fortunately for us, there is a component in which we can use it. And besides all the cool stuff you can do with Python, there are 2 important features which are the ones we're gonna focus in, which are the node encode feature that will allow us to use all our Grasshopper components as functions we can use in our text editor to create really powerful and convenient scripts, and also the parallel functions that will help us take advantage of all our computer cores with the multithreading function that it has, which will make algorithms that consume a lot of computer power to perform much better. Okay, so this Python component is currently not part of the standard components that come with Grasshopper, so we're gonna have to go ahead and download it, but don't worry, it's actually something very easy. All you have to do is go to food4rhino.com/project/ghpython, and you'll be directed to this website where you can actually find tons of plugins and extensions for Rhino and Grasshopper. So then you have to go ahead and create an account with your email, and once you're logged in, if you scroll down, you'll see different versions that have been created for this component. So you're gonna click on the most recent one that says download over here. And as you can see, a file with the extension .gha will be downloaded. Then to install it, you're going to have to go to Rhino and then open your Grasshopper. Then you're gonna go to your Files tab, and then under our special folder options, you're gonna select the component folders. And a new window will appear showing the different plugins and components you have in your system. So what you need to do is to simply drag the file you have downloaded into this folder. So in my case, I have already installed it here. Then you're gonna have to close and restart Rhino, and once you've done this, you're gonna go to your Math tab, and then under your script subcategory, you'll notice that you'll have this Python script available.